Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind, and knowledge becomes a soft lullaby for the night. Tonight's journey will take us across the vast and varied worlds of our solar system, but before we drift into Martian dust and Saturnian rings, before we chase comets and listen to the silence of interstellar space, we begin where all great journeys do, right here at home. Not the kind of home with walls and windows and cups of warm tea, but the grander version. Earth, the pale blue dot, the spinning stone wrapped in air and ocean, gently orbiting an average star in a spiral arm of a rather ordinary galaxy. It's easy to forget in the noise of everyday life that we are already floating in space. You don't need to board a rocket to leave the Earth. You're already on one. But it's only when we began to look back from a little farther away that we started to understand just how delicate and extraordinary this home truly is. In 1972, the crew of Apollo 17 took a photograph that would become known simply as the Blue Marble. It shows Earth suspended in blackness, awash in clouds, continents, and the deep blue of ocean. There are no borders in this image, no sound, no movement, just a world, whole and shimmering. Then in 1990, the Voyager 1 spacecraft, having nearly left the solar system, was commanded to turn its camera around and take one last photograph. In that frame, Earth appears as a tiny dot, a mere pixel, bathed in a scattered beam of sunlight. Carl Sagan, who helped inspire the image, called it the pale blue dot. His words would later remind us that everything we have ever known, every joy, sorrow, war and dream, took place on that small mote of dust suspended in a sunbeam. From these early images, something subtle but powerful began to shift. For the first time, humanity wasn't just looking out into the cosmos, it was looking back. Not to see what it had left behind, but to truly see itself in context. There's a name for this change in perspective. It's called the overview effect. Astronauts who've seen Earth from orbit often describe a kind of quiet epiphany, a wave of understanding that comes not from analysis but from awe. From above, the world doesn't seem chaotic or cruel. It seems whole, fragile, silent. And when you're looking at Earth from the Moon, from orbit, or from a distant spacecraft drifting past Neptune, it doesn't seem like a place that could ever take anything for granted. This new way of seeing, gentle, expansive and humbling, became the philosophical backdrop for space exploration. The farther we travelled, the more we saw Earth as interconnected, alive and profoundly rare. And yet, while our eyes were turning outward, our instruments were also quietly observing home. Satellites began to circle Earth, not just for communication or weather forecasts, but to understand how this planet breathes. They measured rising and falling of the oceans, the warmth radiating from deserts and forests, the gentle flicker of chlorophyll in spring and its dimming in winter. They watched the atmosphere thin slightly each year, like a slowly fading whisper. They listened as glaciers cracked and retreated, and as rainforests shrank, their silence growing louder. It was in many ways a two-way mirror. We studied other planets to learn what might lie ahead for us, and we studied Earth to understand where we truly stood. Venus, swaddled in thick clouds of carbon dioxide, scorched by a runaway greenhouse effect, became a kind of cautionary tale. Mars, once likely wet and warm, now cold and barren, told stories of climate collapse written in rust and sand. Even the moons of distant gas giants offered parallels. Titan, with its methane rains and hydrocarbon lakes, felt like a strange echo of Earth's own water cycle. Enceladus, spraying saltwater geysers into space, reminded us that life may not need sunshine, it may only need warmth and water in the darkness. And so, as our spacecraft coasted through space, some no larger than a piano, others barely the size of a suitcase, they carried more than cameras and computers. They carried a question: are we the only ones? Not just in the cosmic sense, not only about life, but about stewardship, about what it means to care for a planet, to see it clearly, and to listen to its changing rhythms. This is where our journey begins, not with engines roaring or countdowns ticking, but with a kind of quiet noticing, with a new perspective that came not from reaching the stars, but from stepping back and realising how precious this one tiny world is. Before we visit Mars and the gas giants, before we fly past frozen moons and dive into hazy atmospheres, let us remember that our voyage is not about escape, it's about understanding. And sometimes, to truly understand where you might go, you must first remember where you came from. So, as you close your eyes and let your mind drift, imagine looking out a small round window. You see a blue curve painted with cloud floating in a sea of black. No engine sound, no breeze, no music, just light, stillness, and a slow rotation. That is Earth, as seen from space. That is home, as seen with new eyes. And that is the beginning of our gentle expedition across the solar system. If you've ever tossed a paper airplane and watched it drift, weightless for a moment before falling, then you've tasted just faintly the desire that has pulled humans toward the stars for centuries. But paper and wind are not enough for the long journey. To leave the Earth, truly leave it, you must build something that flies not because of air, but despite its absence. And to stay out there, coasting quietly in the dark, you must learn to whisper to the void in a language made of light, magnetism, and patience. This is the story of how we learned to fly without wings. The earlier spacecraft were crude by today's standards. Boxes of metal bolted together, barely able to steer themselves, and equipped with instruments that now feel almost quaint. But their simplicity didn't make them foolish. They were brave in their own way. Mariner, Pioneer, and the earliest Soviet probes didn't need to be elegant. They only needed to reach beyond. Their strength came not from sophistication, but from audacity. Over time, though, our tools grew quieter and more refined. Rockets, once beasts of smoke and thunder, gave way to the gentle murmur of ion propulsion systems. These don't roar like traditional engines, they hum. An ion engine works by charging particles, xenon usually, and accelerating them out the back of the craft. It's a slow push, not much stronger than the weight of a sheet of paper resting in your palm, but in space, with no resistance that push accumulates. Over days, weeks, even months, a spacecraft propelled this way can build up astonishing speeds, all from a continuous exhale. It's less like throwing a spear and more like gliding on a breath. Then there's the matter of power. In the darkness between planets, where sunlight grows thin, solar panels unfold like patient petals, catching what light they can. For missions farther out, beyond Mars, where the sun becomes more of a suggestion than a source, nuclear batteries take over. These radioisotope thermoelectric generators, or RTGs, don't explode or blaze. They simply stay warm. Inside, radioactive decay keeps a steady trickle of electricity flowing, enough to run heaters, computers, and cameras on moons where the cold could freeze steel. The instruments we send with these spacecraft are also marvels of quiet genius. Spectrometers, for instance, don't look at things the way our eyes do. They dissect light itself, splitting it into spectra to read what elements are present, how fast they're moving, and how much energy they contain. To a spacecraft, a planet is not a photograph but a song, and spectrometers are the ears that listen for the harmony of hydrogen, the whisper of methane, the chorus of iron and carbon and salt. Radar systems peer beneath clouds and even ground. Magellan, for example, mapped the surface of Venus not by seeing it, but by bouncing radio waves off its surface and timing their echoes. Like bats navigating caves, these waves revealed mountains, plains, and long-dead volcanoes, all hidden beneath sulfuric skies. Other missions use magnetometers, long thin sensors mounted on booms, gently probing the invisible fields around planets, looking for swirls of charged particles, loops of energy, or the traces of magnetic cores. These instruments never touch the worlds they study. They simply float, observe, and translate. And then, of course, there are the cameras. Spacecraft cameras are rarely about beauty, though beauty often sneaks in. They're designed to count pixels, measure wavelengths, and track changes. But through them we have seen sunrise on Mars, rings casting shadows on Saturn, and the icy plains of Pluto glowing faintly in twilight. Each photo, transmitted over millions of kilometres of emptiness, is a message not just from the probe, but from the planet itself, saying, "I am here, I am real, I have waited to be seen." Perhaps the most poetic part of all this technology is its longevity. Many of our probes live longer than expected, like old explorers refusing to come home. Voyager 1 and 2 were launched in the late 1970s and were only expected to last a few years. Today they are still moving, still sending signals, now drifting through interstellar space where the sun's influence grows faint. Their messages are faint too, carried by ancient transmitters and received by enormous radio dishes on Earth. It takes more than 20 hours for a signal to reach us, and yet we still listen. These spacecraft are not just machines, they are time travellers. They carry golden records, etched with images, music and greetings in dozens of languages, just in case someone somewhere someday finds them. It's not likely, but it's possible, and that possibility is part of the beauty. We often think of engineering as rigid and cold, full of numbers and steel, but in space exploration it is something softer. Every antenna, every solar panel, every thruster is built with a kind of faith. Not just in science, but in the idea that curiosity matters, that sending a small machine across 100 million kilometres to float silently over a frozen moon is somehow worthwhile, that questions we can't yet answer are still worth asking, and that even a robot can be a kind of ambassador. So when you think of spacecraft, try not to picture hulking machines or bolts and wires. Imagine instead a delicate kite coasting through darkness. Imagine a lantern, quietly flickering with data, holding its course not with brute force, but with the careful balance of mathematics and starlight. These are our tools, yes, but they are also our poems, woven not from rhyme, but from trajectory. As you drift further into sleep, let your mind float with them. Across the silence, past the pull of gravity, past the warmth of the earth. Let yourself be carried by a whisper of xenon, a beam of sunlight, or a golden record spinning gently in the dark. The universe does not demand noise or speed. It responds just as well to quiet persistence. And in that stillness we are learning slowly to fly. If you were to stand in a quiet museum gazing into a mirror framed in brass, you might first see your own face, but slowly, if you looked deeper, you'd begin to notice what stands behind you. The walls, the paintings, the way the light from the ceiling lands softly on the floor. The mirror doesn't change what's there, it simply reflects it in a way that makes you see again. In many ways, our solar system is a mirror. As we travel outward, past the warm cradle of the Earth, past the dancing moons and dusty plains, we do not just learn about other worlds. We see, in fragments and in contrast, who we are and what we might become. Among all the planets, Venus is the one that feels the most like a ghost story told to children who take the sky for granted. It is nearly the same size as Earth, and its orbit not so distant. For a long time, it was imagined as our sister world, perhaps cloud-covered but verdant, a place of rainforests and shimmering oceans wrapped in mystery. But when we finally sent probes like Venera and Magellan to peer through the veil, what they revealed was not life, but warning. Venus is shrouded in thick clouds of carbon dioxide and sulfuric acid. Its surface is hot enough to melt lead. The air pressure would crush a submarine, and yet the strangest part isn't that it's so inhospitable, it's that it might not have always been this way. Some planetary scientists believe that Venus once had water, that perhaps, for a time, it was mild, even stable. But then something changed. A tipping point was passed, and the greenhouse effect spiraled out of control. The oceans evaporated, the clouds thickened, the heat rose and then never left. Venus became a slow-motion furnace. Today, standing there, if such a thing were possible, would be like walking into the memory of a habitable world. And in that memory, Earth catches its reflection. It reminds us that stability is precious, not guaranteed. That climate, once tipped, does not always tip back. When we study Venus, we're not just looking at a distant planet. We're seeing one version of Earth's future that was never meant to arrive, but might, if we forget to listen. Mars offers a different kind of mirror, not one of caution, but of longing. Where Venus is dense and choking, Mars is thin and silent. Its skies are dusty pink, its ground rusted red with iron oxide. But here too the past whispers, the ancient riverbeds that crisscross the surface, the mineral traces of clays and salts, the layered cliffs and dried out craters, all suggest a time when Mars was not barren. There is compelling evidence that it once held water in abundance, lakes, perhaps seas. Some believe that it had a magnetic field long ago, that it might have held onto a thicker atmosphere, one that could cradle warmth. What happened then? Perhaps its core cooled too quickly. Its magnetic shield vanished, and with it, the atmosphere slowly drifted away into space, stripped by solar wind. Water evaporated or froze beneath the surface. Life, if it ever began, had nowhere left to grow. Mars became a planet of stillness, not because it failed, but because it changed. We don't yet know the full story, but every probe we send, every rover that rolls across its dusty plains, seems to be asking the same question in 1,000 quiet ways. Could it have been like us? And if so, are we glimpsing our own past, or one possible future? These comparisons are not just poetic, they are practical. The field of comparative planetology exists because, by studying the geology, atmosphere and climate of other planets, we sharpen our understanding of Earth itself. Our home becomes clearer not by staring only at it, but by stepping back and placing it alongside others. From the gas giants like Jupiter and Saturn, we learn about gravity's influence on formation. From Mercury, we see how proximity to the Sun affects atmosphere retention. Even tiny icy Pluto, with its nitrogen glaciers and changing atmosphere, offers insight into seasonal cycles at the edge of possibility. And then there are the moons, so many moons. Titan, orbiting Saturn, has lakes and rivers made not of water, but of liquid methane and ethane. Its atmosphere is dense and organic molecules drift down like snow. In some ways, Titan is the only other place in the solar system where it rains. Enceladus, bright and frozen, hurls geysers of salt water and organic compounds into space from cracks in its south pole, hinting at a warm subsurface ocean. These places are cold, yes, but not dead. They remind us that life, if it is to be found elsewhere, might not need Earth-like conditions. It might survive in oceans beneath ice, or in clouds high above scorched ground. And if life can adapt to those extremes, it reminds us that Earth, so mild, so stable, so welcoming, is an even greater treasure than we thought. There's a kind of empathy that grows from this planetary perspective. It doesn't shout or argue, it just quietly asks us to pay attention, to see what can go wrong, what might have gone right, and what can still be preserved. Studying these worlds helps us imagine not only other ways of being, but also better ways of belonging here. So the solar system, in the end, is not just a collection of planets and moons, it is a gallery of fates, a mirror with many faces, a soft-spoken reminder that the universe is wide but not indifferent, that it offers us warnings and wonders alike, and leaves it up to us to listen gently. Tonight, as you settle deeper into rest, know that each time we send a craft across that star-filled dark, we are not just searching. We are learning to see, through distant clouds and ancient dust, our own reflection, framed in orbit, softened by time. If you were to walk the surface of Mars, not in a pressurized suit with humming instruments, but quietly, as though it were a familiar place, you might find yourself standing beside the ghost of a river. The stones underfoot are smooth in places. The shape of the land curves like a valley worn not by wind but by water, and the surface is scarred with meanders and fans. There are no ripples, no glimmers, no sound of water moving over rock, but the shapes remain, like echoes frozen in ochre dust. This is the Mars we've come to know, not a world of flowing streams, but one that remembers. Long before the word Mars was etched into mission logs, long before our cameras first glanced across its rust-red skin, people had imagined it. Some saw canals, some saw life, some imagined warlike civilizations, others imagined barren deserts. But the truth, as it often does, turned out to be more complex and more beautiful. Our first gentle touch came with Viking in the 1970s. 2 landers, twin explorers, touched down and began transmitting images and data. The landscapes were quiet, pebbled plains, distant hills, reddish haze, but they were unmistakably alien. The soil held secrets. The sky, pinkish and strange, shifted in ways we hadn't expected. But the data suggested something ancient had happened, something wet. The Viking orbiters saw channels and valleys that did not fit the dry, frozen world we saw now. The land seemed shaped by something softer, something that once moved and pooled. Years later, Pathfinder and its companion, the tiny rover Sojourner, gave us motion. For the first time, something rolled across Mars. It wasn't fast, but it was free, and what it saw told a story that deepened with each generation. Rocks were rounded, not jagged, tumbled by water, not carved by wind. Some were embedded in patterns, as if they'd been carried and dropped by gentle currents. These clues weren't shouts, but whispers. Mars didn't need to be loud to be persuasive. Then came Spirit and Opportunity, twin rovers sent to different sides of the planet in 2004. They were expected to last 3 months. One survived for over 6 years, the other for nearly 15, and in that time they transformed what we understood about the Martian past. Opportunity rolled into a crater and found layers of rock, thin parallel bands like pages in a geologic diary. Some of these layers contained tiny round structures nicknamed blueberries, hematite spherules, likely formed in water. Elsewhere, Spirit found silica-rich soils near an ancient volcanic vent. Again, something that would typically form in the presence of water. These weren't just visual hints anymore. They were chemical signatures, molecular confessions. Mars had been wet, repeatedly, perhaps even for millions of years. These rivers didn't just flow, they pooled. They formed deltas, spread sediment, shaped basins. Some regions, like Gale Crater and Jezero Crater, appeared to have once hosted lakes, wide and placid, rimmed with sediment fans that could rival Earth's own river deltas, and where there were lakes there might have been shorelines, and where there are shorelines, life, tiny, microbial, stubborn, sometimes finds a way. But today, of course, there is no liquid water on the Martian surface. The pressure is too low, the temperature is too cold. Any water would boil away or freeze solid. Yet beneath the ground, trapped in minerals or as subsurface ice, water remains. The planet has not forgotten entirely. Mars also breathes in its own way, not with lungs, but through its seasons, its shifting winds and swirling dust. The Martian year is nearly twice as long as ours, and during its warmer months, dust storms can rise up and envelop the entire planet in a reddish haze. The sky darkens, the surface cools. Solar panels fall quiet under a settling blanket of powder. But even here, in this seeming lifelessness, there is rhythm. The poles grow and shrink with carbon dioxide frost. Clouds form high in the thin atmosphere, sometimes water ice, sometimes dusty and strange. Sunsets are blue, not red, because of how fine dust scatters sunlight. The air is cold, whisper-thin, and carries only a fraction of the force we feel on Earth. But it moves, it dances, and it remembers. What Mars lacks in comfort, it offers in clarity. Its surface is not hidden by jungles or oceans. Its history lies bare. You can see time here, not through ruins or fossils, but through rock, battered, layered, waiting. Every hill is a page, every crater is a question, and every mission we send becomes a kind of archaeologist, brushing away dust with wheels, drills, and patience. Spirit and opportunity didn't find cities, they didn't find fossils or plants, but they found context. They found enough to suggest that Mars was not always as it is now, that its silence is not eternal, but earned, that what we see is not a failure, but a shift. The world may have once flowed, it may have hosted chemical ingredients for life, and if it didn't, it came heartbreakingly close. Tonight, as you let your mind drift, imagine standing in a dry Martian riverbed. The stones are small, smooth, reddish. Above you the sky is dim, tinted lavender near the horizon. There's no sound. There is stillness, ancient, undisturbed, unhurried. Somewhere far above, Earth rises as a bluish star, and under your feet, in the dust, is a story billions of years old, unread, unspoiled, and still waiting for its next chapter. If spirit and opportunity were the twins who taught us how to listen to Mars's past, then curiosity was the one who began asking deeper questions, not just what the planet had been, but whether it could ever have hosted life. Launched in 2011 and landing in 2012, the Curiosity rover is no longer just a wandering geologist. It is a patient investigator, carefully turning over stones, studying chemistry, sniffing the air, and digging into time itself. And in Gale Crater, a place chosen because it might once have held a lake, Curiosity has been slowly, steadily uncovering clues. It found the expected, sedimentary rocks, ancient lake bed signatures, fine layers that hinted at repeated wet-dry cycles. But it also found something more intimate, traces of organic molecules, the building blocks of life. Now, this doesn't mean life was there. Organic molecules can be formed through both biological and non-biological processes, but their presence is like the scent of bread in a kitchen. You can't say who baked it, or even if anyone did, but you know something happened. The molecules Curiosity discovered were complex enough to suggest a world once capable of sustaining life, at least for a time. In some rock layers, these compounds were more concentrated, hinting at cycles or perhaps preservation by certain minerals. But even more intriguing than what was found in the rocks was what was occasionally found in the air. Mars, for the most part, has a very stable atmosphere. Thin, mostly carbon dioxide, with only trace amounts of other gases. But Curiosity's instruments detected something strange. Methane. Not constantly and not predictably, but in little puffs. Seasonal increases, spikes at certain times of year, and sudden bursts that faded as mysteriously as they came. On Earth, methane can be produced biologically, from microbes in wetlands or the digestive systems of animals, but it can also come from geologic sources, reactions between water and certain types of rock, or the slow release of trapped gases from underground. What made the Martian methane so compelling wasn't just that it existed, but that it appeared to change with time. In Martian summer, levels rose. In winter, they dropped. This rhythmic exhalation raised an eyebrow. It felt like breath. Not of a person, perhaps, but of a world. something beneath the surface, something hidden, was releasing it. Whether this something was alive or merely warm rock meeting frozen water remained unknown. Other instruments, like those on the trace gas orbiter orbiting Mars, have tried to confirm these findings, but the picture remains complex. Some measurements detect nothing. Others align with Curiosity's spikes. It's a mystery, not one to be solved quickly, but one that lingers, like a question asked in a whisper. And it's not the only question. Mars also contains ammonia in small amounts, another molecule that, while not proof of life, is often associated with it. Ammonia breaks down quickly in ultraviolet light, so its presence suggests it's being replenished somehow. Could there be underground pockets still venting it slowly? Could there be a kind of chemistry we don't yet fully understand? The truth remains slippery. Even the soil holds its riddles. Perchlorates, reactive chemicals that make life difficult, are present in many samples. They can destroy organics but also potentially preserve them, depending on conditions. It's a bit like finding both the lock and the key buried together, unsure which came first. And this, in many ways, is the nature of Martian science. One discovery uncovers another layer of mystery, not a solution. To answer these riddles, we needed to go further, not just to analyse, but to prepare to return samples to Earth. That's where Perseverance, Curiosity's younger cousin, comes in. Landing in Jezero Crater in 2021, Perseverance was sent to a place that once held a vast delta. Clear evidence of standing water, sediment deposits, and perhaps the conditions suitable for life. With new tools, more sensitive instruments, and a storage system for collecting samples to eventually bring home, Perseverance represents a step not just in curiosity but in commitment. We are no longer satisfied to study from afar. We are preparing to hold Mars in our hands, grain by grain. One of Perseverance's first tasks was to begin sampling rock cores from ancient lakebed deposits. These cores, carefully sealed in tubes, will wait until a future mission retrieves them. This will be the first time we bring Martian surface material to Earth, where we can study it with the full weight of human laboratories, microscopes and imagination. It's a kind of scientific time capsule, and it's also a trust exercise, with the future, with the technology we've built, and with the planet itself. But perhaps the most poetic part of Perseverance's mission is not what it drilled or measured, but what it launched. Tucked beneath its belly was a small companion named Ingenuity, a helicopter no larger than a box of tissues, designed to fly in the thin Martian atmosphere. When it lifted off for the first time, it became the first powered aircraft to fly on another planet. Its blade spun incredibly fast, over 2,000 revolutions per minute, to catch what little air existed. It hovered, dipped, danced, and returned, light as a feather. That first flight was only 39 seconds long, but it changed everything. Ingenuity was only supposed to fly 5 times. It's now flown dozens more. Each journey expands the possible. It scouts terrain ahead for Perseverance, tests navigation systems, and offers us a new way of seeing, gliding gently above red sand and ancient rock, like a bird made of carbon fibre and dreams. These rovers, Curiosity, Perseverance and their companions, are not just machines. They are the quiet questions we've launched into the dark. Each wheel print in the dust is a punctuation mark in a sentence we're still writing. And while they do not speak in language, they tell stories of rivers long vanished, of air that holds secrets, of rocks that crumble and whisper. So tonight, let your thoughts follow a rover, across rusted plains, beside a ridge where water once flowed, beneath a lavender dusk sky. Imagine it pausing, camera tilted slightly as if listening, and perhaps, if you're quiet enough, you'll hear what it hears. The steady exhale of an ancient world breathing mysteries into the thin wind. It's one thing to send a machine to another planet. It's another thing entirely to land it gently. And to do that on Mars, A world with just enough atmosphere to cause problems, but not enough to slow you down safely with a parachute alone, requires an unusual blend of mathematics, creativity, and what could only be called quiet bravery. Over the years, as we've learned more about Mars, our landings have become more ambitious, not just in where we land, but how. The earliest landers arrived with the brute simplicity of parachutes and crash cushioning shells. They didn't try to be elegant, they simply had to survive. The Pathfinder mission, for instance, used giant airbags that inflated before impact, allowing the probe to bounce, yes, bounce, across the Martian surface before settling into a stop. It worked, even if it looked clumsy. But as missions grew more precise and the terrain more complex, we needed to evolve. When it came time to land the Curiosity rover, a machine the size of a small car, NASA engineers unveiled something that seemed, at first, like science fiction: the Sky Crane. In this system, a descent stage equipped with retro-rockets would hover just above the surface and slowly lower the rover down on nylon cords. Once the wheels touched ground, the cables would be cut, and the Sky Crane would fly away to crash at a safe distance. It sounded absurd, it worked perfectly. The same method was used again for Perseverance, and by then, what once seemed bizarre had become a symbol of quiet engineering elegance. To lower a rover like a gift onto the sands of another planet using gravity and fire and fabric is a kind of dance. And each time we do it, we learn to dance a little more gracefully. But we haven't just landed rovers, we've learned to listen. And in 2018, the InSight lander brought to Mars a seismometer, a finely tuned ear pressed gently against the skin of a silent planet. What it heard was not silence at all, it was Mars quakes. Unlike Earth's tectonic shifts, which are often driven by moving plates, Mars quakes come from cooling and contracting rock. The planet is still settling, still shrinking very slightly as its interior loses heat. These quakes are usually small, quiet tremors rather than shouts, but they reveal a great deal. The way the waves move through the planet helps scientists infer what lies beneath the surface, how thick the crust is, whether the core is liquid or solid, and how layered the mantle might be. Listening to a planet is a deeply intimate act. It's one thing to photograph it, another to study its soil, but to listen is to feel its pulse. And Mars, it turns out, has a steady heartbeat. Not loud, not violent, but present, rhythmic, persistent. We've also started to listen in another way, not just to the deep rumble of the interior, but to the soft movements of the air itself. The Perseverance rover carries a microphone. At first, it was a simple addition, meant to capture the sound of landing, but it remained active afterward, giving us something we'd never had before, the soundscape of another world. The recordings are sparse, a low hum, the pop of static from electrical systems, the crunch of wheels rolling over pebbled terrain, and then, perhaps most hauntingly, the wind, a thin, high whisper. Not the kind of wind that bends trees or howls through valleys, but a colder, lighter cousin. On Mars, the atmosphere is only about 1% the density of Earth's. That means sound travels differently, more faintly, more hollow. Yet still it travels. For the first time, we could hear a breeze drift across alien dust. We could listen to the sigh of a planet that, for so long, had only spoken in light and shadow. The audio was cleaned, filtered, enhanced. It was brief, but it was real. You might wonder, why does this matter? After all, we've known so much about Mars from images, from data, from chemistry and math. What does wind add? The answer, as it so often is with space exploration, lies not just in science, but in connection. To hear Mars is to feel Mars. It's no longer a distant diagram in a textbook, or a circle on a classroom mobile. It's a place with atmosphere, with sound, with rhythm. A place where wind sighs across ancient stone and robots rumble gently toward new horizons. A place that can speak in its own quiet way. Even the dust devils, Those swirling columns of air that sometimes race across the plains leave their signature on the sound recordings and seismometers. We can't see them directly most of the time, but we know they pass, like fleeting ghosts. We hear the drop in air pressure, the subtle swish of particles, the delicate vibration of a machine that knows it is being touched by wind. And while we listen, we also begin to feel for these machines. They are not alive, but they endure. They do not sleep, but they pause, they wait, they wake. We assign them names, we track their journeys. When they stopped responding, when spirit fell silent, when opportunity didn't wake from a global dust storm, we grieve quietly, as though saying goodbye to an old friend. There is something deeply human about sending a machine millions of kilometres away to explore a world it cannot touch, then sitting silently on Earth and waiting for its whispers to return. Each ping of data is a letter, each new photograph, a postcard, each second of audio, a voice message from a companion made of circuits and solar panels. So as we close this chapter on Mars, as we listen one last time to the distant wind and the crunch of rover wheels, let us remember, the greatest discoveries are not always the ones that shout. Sometimes they arrive like a breath, a tremor, a hum, and sometimes they arrive on a breeze from a planet that waited patiently to be heard. To travel to Saturn is to drift into a deeper kind of quiet. The sunlight fades. The cold settles in, and everything slows, not in the sense of delay, but of serenity. Saturn doesn't shout for attention. It rotates, rings gleaming, storms coiling in its cloud tops, as though it's always been that way, an ancient, distant monarch spinning slowly beneath a crown of ice. For many years we could only admire it from afar, a blurry circle, a mystery adorned with stripes. Then, in 2004, a spacecraft arrived. It had travelled nearly 7 years to get there. Its name was Cassini, and what followed was not a brief visit, but a long devoted companionship. Cassini didn't just fly by Saturn. It stayed. It orbited. It circled again and again, weaving between moons, diving through ring gaps, sending back images and data that turned the planet from symbol into place. In total, the spacecraft spent 13 years in the Saturnian system, and during that time, it became something more than an instrument. It became a listener, a chronicler, and eventually a guest who knew it was time to leave. Saturn itself is a world of layers, hydrogen, helium, and haze. It has no solid surface, only a gradual transition from sky to fluid, and winds that roar faster than any on Earth. Every few decades a great storm rises from its depths, so vast it can wrap around the entire planet, crackling with lightning, leaving a pale scar in its wake. Cassini saw one of these tempests unfold, a spiralling tower of violence rising through pale clouds, then disappearing again into the calm. And then there's the hexagon, a vast six-sided storm pattern at the planet's north pole, perfectly geometric, persistent. It defies easy explanation. The shape remains stable, year after Saturnian year, as though the planet is wearing a badge from some ancient unknown order. It's not an illusion or an accident of light. It's real, a hexagon made of wind. But perhaps what Cassini revealed best was the riddle of Saturn's rings. Made mostly of water ice, the rings are thin, delicate structures that span tens of thousands of kilometres, yet are often no thicker than a building. They shimmer and shift, forming waves and patterns as tiny moons shepherd them from within. At a glance, they seem eternal. But Cassini helped confirm that they are young, perhaps only 100 million years old. In cosmic terms, they're recent, more ephemeral than once imagined. The rings are not the planet's inheritance, but its ornament, possibly the remains of a shattered moon or icy body pulled too close. Cassini passed through the shadows of the rings and looked outward, catching a famous image, Earth, once again, as a dot. A pale blue speck beneath the rings, backlit by sunlight, suspended in blackness. Just as Voyager had done decades earlier, Cassini reminded us how small we truly are, and how astonishing it is that we can even look back at all. Saturn also holds one of the most powerful magnetic fields in the solar system, one that swirls charged particles into glowing auroras that dance over its poles. Cassini watched those too, ultraviolet flickers shifting in the night side of the planet, invisible to human eyes but clear to its sensors. These auroras are not just lights, they are signals, pulses from a world that, though gaseous and distant, hums with energy and rhythm. Over the years, Cassini also visited the moons of Saturn. Over 80 known, many strange, many beautiful. We'll spend more time with Titan and Enceladus in the next session, but even the smaller moons held surprises. Some were covered in deep canyons, some were smooth, others jagged. A few seemed to dance in resonance, their orbits tugging gently on one another in a gravitational waltz that has lasted billions of years. But eventually, as all journeys must, Cassini's mission reached its end. The spacecraft was running low on fuel, not power, but the ability to steer. And so, a decision was made. Rather than let it drift uncontrolled, risking accidental contact with a moon that might harbour life, Cassini would perform one last task, a grand finale. It would dive. In a series of carefully planned orbits, Cassini threaded the narrow space between Saturn and its innermost ring, places no spacecraft had ever flown before. It passed just 2,000 kilometres above the cloud tops, collecting unprecedented data, seeing the planet as no other machine had. And then, on September 15th, 2017, it entered Saturn's atmosphere. Slowly at first, then faster. The pressure rose, the heat built. The spacecraft began to tumble, to burn. It sent data until the last moment, until the signal faded. There was no crash, no impact. Cassini dissolved. Its atoms scattered in the very world it had studied for over a decade. It became, in the softest possible way, a part of Saturn. There's something deeply human in that ending. Cassini didn't shut down, abandoned. It completed its work, bowed, and stepped into the clouds. The choice to destroy it wasn't cold. It was careful. It was gracious. It was made because the possibility of contaminating another world, of disrupting something we might not even understand, was too great. That's a kind of respect, not just for science, but for the unknown. So tonight, if your thoughts are still drifting, picture a spacecraft alone in a vast orbit, looping between rings and moons, catching light on its solar panels, watching storms from 1,000 kilometres up. And then imagine it turning downward, not falling, but descending on purpose, into clouds it once only circled. Not with fear, but with peace, with purpose, with everything it had seen encoded in its final signal. A farewell, not just to Saturn, but to us. Some of the quietest places in the solar system are also the most promising. While gas giants like Saturn roar with storms and spin with blinding speed, two of its moons, Enceladus and Titan, drift like secrets wrapped in ice. They do not look like homes for life. They do not advertise warmth or abundance, but beneath their frozen silence there are stories unfolding, stories of oceans beneath crusts, of chemistry in clouds, of worlds that whisper rather than shout. And the more we listen, the more these moons begin to feel less alien. Not Earth-like exactly, but familiar in a deeper way, as if the conditions for life might not be unique but quietly replicated in places far colder than we ever imagined. Let's begin with Enceladus, a small moon only about 500 kilometres across, no wider than the state of Arizona or the country of Wales. From a distance it looks unassuming, bright white, heavily cratered, frozen through. But in 2005, during one of its close passes, the Cassini spacecraft saw something extraordinary. Near Enceladus's south pole, the surface isn't solid and still. It's fractured, crisscrossed with long blue lines that glow faintly in infrared. From those cracks, now called tiger stripes, something was erupting. Plumes, geysers of salt water, speckled with organic molecules shooting up into space at hundreds of meters per second. These weren't one-time events, they were persistent, rhythmic, like breath. Cassini flew through those plumes, not once but many times, and it sampled them. What it found wasn't just water, it was warm water, rich in salts and compounds that, on Earth, are associated with hydrothermal vents. There was hydrogen gas too, likely produced from chemical reactions between rock and hot water in the moon's interior, reactions that, on Earth, power entire ecosystems deep beneath the sea where sunlight never reaches. This is what makes Enceladus so hauntingly compelling. Beneath a shell of ice lies a global ocean, warmed not by the sun but by tidal flexing, the gravitational pull of Saturn kneading the moon's interior, generating heat through friction. This is an ocean world in the shadows, and if it has water, warmth and organic chemistry, three key ingredients for life, then something may be stirring there, hidden from view, quietly thriving beneath kilometres of ice. We do not know, we cannot yet say, but the possibility is profound. And then there is Titan, the second largest moon in the solar system, even bigger than Mercury. If Enceladus is a glinting ice marble, Titan is a world wrapped in gold. Its thick atmosphere is rich in nitrogen and shrouded with orange haze, giving it the appearance of a planet constantly caught in twilight. Unlike any other moon, it has weather, clouds that drift, rains that fall, rivers that carve the surface. But the rain on Titan is not water, it is methane, liquefied by the moon's frigid temperatures. The rivers are methane. The lakes and seas, yes, it has seas, are made of methane and ethane, glistening in the cold. Titan is the only place in the solar system, other than Earth, known to have stable liquids on its surface. But here the chemistry has changed. It's a mirror world, flipped and strange. Despite this difference, Titan is deeply Earth-like in shape and mood. Its rivers meander, its lakes have shorelines, its clouds gather and disperse in seasonal rhythms. Cassini mapped these features with radar, peering through the haze to find mountains, dunes and coasts. One sea, Kraken Mare, stretches over 1,000 kilometres wide. It even has waves. And below all of this, beneath the methane rain, the hydrocarbon dunes, the nitrogen fog, scientists believe Titan may have a subsurface ocean of water hidden beneath its icy crust. If true, that means Titan contains two worlds, one on the surface, sculpted by alien rain, and one below, warmed by tidal forces and sealed in silence. What could be happening in those hidden waters? Could there be life, not as we know it, but adapted to cold and chemistry? Could the upper atmosphere's complex hydrocarbons drift down, mix into the ocean below, and give rise to something utterly foreign yet faintly familiar? These questions are not idle. They shape missions. In the coming years, NASA will launch a mission called Dragonfly, a robotic rotorcraft designed to fly across Titan's surface. Like a drone drifting through golden haze, it will hop from site to site, studying the chemistry, the weather, and possibly the surface composition. It will explore not just as a machine, but as a storyteller, gathering pieces of a world that resembles a dream of Earth viewed through frosted glass. Both Enceladus and Titan challenge our assumptions. For so long, we believed that life required sunlight, warmth, and Earth-like conditions. But here, in the frozen reaches of the outer solar system, are places where life might not need light, where warmth comes from within and oceans lie hidden beneath silence. If life can exist in these shadowed places, Then it becomes less of a miracle and more of a pattern, emerging wherever the right chemistry meets the right conditions, regardless of sunlight or scenery. These moons also teach us something quieter. They remind us that what appears lifeless may only be hiding, that silence is not the same as absence, and that sometimes the most astonishing things are kept just beneath the surface, waiting for us to listen, to believe, and to return. So as you rest now, drifting gently through your own inner sea of thought, imagine hovering above Titan's golden clouds, methane lakes stretching out below, or gliding past Enceladus as it exhales icy vapour into the void. These are not places of noise or drama. They are places of whispers, and somewhere in those whispers the universe may be telling us its quietest secret, that we were never truly alone. Jupiter doesn't ease into view. It arrives in the imagination like a thunderclap, vast, striped, blazing with bands of amber, beige and crimson. It dominates not only the sky but the solar system itself. It is more massive than all the other planets combined, and though it lacks a solid surface, it has presence, a kind of deep, ancient gravity that makes it feel more like a force than a world. For centuries we saw it only as a shifting disk through telescopes. But then we went there, and what we found was not just a planet, but a swirling masterpiece of chaos, rhythm, and mystery. The first close encounters came with Pioneer 10 and 11, then Voyager 1 and 2, and later Galileo, which orbited Jupiter in the 1990s. Each mission peeled back a layer, revealing more than just clouds and colour. They saw lightning brighter than any on Earth, radiation belts that could fry a spacecraft's electronics in minutes, and auroras that dance not just near the poles, but sometimes across vast arcs, fueled by the planet's immense magnetic field. But one feature above all captured the imagination: the Great Red Spot, a storm larger than Earth, swirling in the southern hemisphere, spinning for at least 350 years, possibly longer. It has changed over time, shrinking, intensifying, sometimes fading, but it has never disappeared. The winds in its outer bands reach nearly 700 kilometers per hour, yet the storm centre rotates with a kind of eerie calm. No one is entirely sure what gives it its ruddy hue, perhaps sulfur compounds, perhaps something yet to be identified. But whatever its composition, it stands as a testament to the power and persistence of planetary weather. And then came Juno. Launched in 2011 and arriving at Jupiter in 2016, the Juno spacecraft was different. Rather than staying far from the planet's radiation belts, Juno dove in again and again on long elliptical orbits that took it within just a few thousand kilometers of the cloud tops. It was built to withstand the storm, armoured and careful, powered not by radioactive decay, but by solar panels, which had to stretch wider than any before to collect enough light this far from the sun. What Juno revealed was astonishing. The colourful bands of Jupiter's surface, once thought to be relatively shallow, extend much deeper than expected, possibly thousands of kilometres into the planet's atmosphere. These belts and zones aren't just surface patterns. They're massive convection currents, rivers of gas carrying heat and chemicals from the deep interior to the outer layers. Some zones rise, others sink. All of them move. Near the poles, Juno discovered something no one had predicted: cyclones arranged in geometric patterns. At the North Pole, 8 massive storms form an almost perfect octagon around a central vortex. At the south, 5 storms spiral in a symmetrical circle. These systems are stable, long-lived, and utterly alien. It's as though Jupiter's storms don't just happen. They organise, choreographed by a physics we don't yet fully understand. Juno also studied Jupiter's magnetic field, the strongest of any planet. What it found defied previous models. Instead of being centred and symmetrical, Jupiter's magnetic field is lopsided, Stronger in some places, weaker in others, tilted, strangely, from the axis of rotation. It suggests that something unusual is happening deep within, perhaps a fuzzy core, not a dense ball of rock, but a mixture of rock and metallic hydrogen, blurred and blurred again by heat and pressure, until no clear boundary remains. Metallic hydrogen, something that doesn't exist naturally on Earth, may be what powers much of Jupiter's magnetism. Under the immense pressure inside the planet, hydrogen atoms are squeezed so tightly that electrons begin to roam freely, making the substance behave more like a metal than a gas. This sea of electrons, rotating with the planet, generates electric currents, and with them an enormous magnetosphere, so vast it could contain the Sun itself. And in that magnetosphere, trapped particles scream around the planet at near-light speeds. These particles slam into the atmosphere, igniting auroras that circle the poles, sometimes brighter, broader, and more intense than anything Earth's northern lights have ever shown. Juno's ultraviolet and infrared instruments captured these displays, revealing structures that pulse with energy, bend with magnetic flux, and sometimes surge in response to changes from Jupiter's own volcanic moon, Io. All of this, the storms, the bands, the magnetic anomalies, paints a picture of a planet in constant, controlled chaos. Jupiter is not solid, but it has structure. It has no surface, but it has depth. Its features don't stand still, yet they persist for centuries. It is a world ruled not by geography, but by dynamics. Layers upon layers of motion, each influencing the next. But perhaps the most striking thing Juno gave us wasn't data or discoveries. It was perspective. From above the North Pole, it sent back images of a side of Jupiter no one had ever seen. Not a flat-banded disk, but a globe wrapped in storms and shadows glowing softly in infrared. It looked less like a planet and more like a living painting, a sphere of perpetual movement, as if sculpted by the wind. So now, if you close your eyes, let yourself imagine drifting just above Jupiter's clouds. Beneath you, the atmosphere churns in slow spirals, orange and cream blending like oil in water. Far below, lightning flickers, brief, brilliant, then gone. You are weightless, soundless, watching as a storm older than your nation rolls slowly on, and a spacecraft no larger than a bus dives again into gravity's grip to listen, to measure, and to quietly learn. Jupiter is not peaceful, but it is beautiful. It is not calm, but it is constant, and in its roiling clouds, we begin to see the shape of other giants, other systems, and perhaps even the kinds of planets that orbit distant stars. But for now, it simply turns, massive, magnetic, mysterious, and we, tiny by comparison, are fortunate just to watch. If Jupiter is a giant symphony of motion, then its moons are the quiet, persistent melodies that play beneath the thunder. Each one is distinct. Each one sings a different part, and together they form a kind of celestial harmony. 4 large voices orbiting in resonance, pulled and reshaped by gravity's relentless rhythm. These are the Galilean moons, Io, Europa, Ganymede, and Callisto. First seen by Galileo in 1610 through a crude telescope, they were the first moons ever observed beyond our own. And even now, more than 4 centuries later, they continue to surprise us, to challenge us, and to gently hint at the possibility that life may exist far beyond Earth's blue shores. We begin with Io, the innermost of the 4, and by far the most volcanic object in the solar system. Its surface is a patchwork of yellows, oranges, and whites. Colours that come not from vegetation or rock, but from sulphur, spewed skyward from active volcanoes that dot the landscape. These aren't rare events. Io is in a constant state of upheaval. Plumes rise hundreds of kilometres high. Lava lakes churn with molten rock. Mountains taller than Everest collapse under their own weight, then rise again as the crust shifts. All of this heat comes not from the sun, but from tidal heating. The gravitational tug-of-war between Io, Jupiter, and its sibling moons flexes the little world like a ball of dough, generating internal friction and heat. It is a strange place to imagine life, so fiery, so unstable, but it reminds us that planetary activity can come from within, and that a world without sunlight can still move, still change, still be alive in its own violent way. Next is Europa, perhaps the most poetic of Jupiter's moons. Smooth and bright, it reflects sunlight with a clarity unmatched by most other bodies in the solar system. From afar it looks like a polished marble, veined with long, brown cracks that streak across an icy shell. But beneath that ice, perhaps only a few kilometres thick in places, lies something extraordinary. A global ocean, kept liquid by tidal heating, encased in darkness, yet possibly filled with warmth and movement. We know this ocean exists not just from surface features, but from magnetic field data. When the Galileo spacecraft flew past Europa, it noticed distortions in Jupiter's powerful magnetic field. Distortions that made sense only if an electrically conductive layer, such as a salty ocean, was moving beneath the ice. Later images showed chaos terrain, regions where the ice appears broken, jumbled and refrozen, as though large chunks of crust had floated on a soft, shifting sea. Europa's ocean could be twice the volume of all Earth's oceans combined. It's possible that hydrothermal vents on the ocean floor release heat and nutrients, just as they do on Earth, creating environments where life could begin or persist without sunlight. If life ever existed, or still exists beyond Earth, Europa may be our best chance of finding it. This is the promise of the upcoming Europa Clipper mission, set to launch in the next few years. It won't land, but it will fly by dozens of times, scanning Europa's surface in exquisite detail, sampling the thin atmosphere, analysing the chemistry of surface ice, and searching for plumes that might be venting ocean material into space. If such plumes exist, and if we can fly through them, they could offer a sample of the ocean below, without the need to drill. And then there is Ganymede, the largest moon in the entire solar system, even bigger than the planet Mercury. Ganymede is a world of contrasts. Its surface is a mixture of bright grooves and darker, older terrain, shaped by ice tectonics and ancient impacts. But the most astonishing discovery is that Ganymede has its own magnetic field, the only moon known to do so. This suggests that deep beneath its surface something is moving, perhaps a liquid iron core similar to Earth's. It's also likely that Ganymede holds a subsurface ocean, though perhaps sandwiched between multiple layers of ice. Ganymede's sheer size and magnetic strength make it a fascinating candidate for future study. It doesn't have Europa's elegance or Io's fireworks, but it hums with quiet potential, a sleeping giant layered with secrets. Finally, there is Callisto, the outermost and most quietly mysterious of the four. Its surface is ancient, heavily cratered, and largely unchanged for billions of years. If Io is fire and Europa is water, Callisto is stone, stable, cold, and slow. But even here, under kilometres of ice, models suggest that a subsurface ocean may exist. Less active, less dramatic, but present. Callisto may not show the signs of heating or geologic change like its siblings, but it may still hold the building blocks of life beneath its stillness. Together, these four moons form a kind of natural experiment. Four worlds born from the same environment, shaped by the same planet, yet utterly different in character. One burns, one glides beneath ice, one carries a magnetic heart, one sleeps, and all of them orbit the largest planet bound together by gravity, history and mystery. Jupiter's moons are not footnotes. They are worlds in their own right, each deserving of attention, each holding a mirror to Earth in a different way. They challenge our definitions of habitability, reminding us that life might not need continents or sunshine. It might survive in saltwater darkness, in chemical warmth, in silence. So as you rest now, drifting slowly through thoughts, picture the orbit of these moons, their quiet paths, their distant faces turned always toward Jupiter, their surfaces glowing faintly in reflected light. Hear, if you can, the slow harmony they play. A storming fireball, an icy whisper, a magnetic murmur, and a sleeping stone. A chorus turning softly, deep in the cold quiet of space. There's something quietly unsettling about Venus. From a distance it appears calm, wrapped in thick golden white clouds that reflect sunlight with a bright pearly glow. It is often the first planet to appear in the evening sky and the last to disappear before dawn. Ancient cultures called it both the morning star and the evening star, and for centuries its brilliance was a symbol of beauty, elegance, and divine presence. But that glow hides something far less serene. Venus is roughly the same size as Earth. It's made of similar materials. It formed in the same part of the solar system. It may have even once had water, oceans, rivers, clouds like our own, and yet it is the hottest planet in the solar system. Not because it's closest to the Sun, but because of what happened to its atmosphere. Venus is not Earth's twin in harmony. It is Earth's warning. A mirror tilted toward a possible future. Our first real encounters with Venus were not gentle. The Venera missions launched by the Soviet Union in the 1960s and 70s were the first to pierce its clouds. These early landers were not expected to survive long. Venus's atmosphere is crushingly thick, over 90 times the pressure of Earth's, and its surface temperature hovers around 465 degrees Celsius. That's hot enough to melt lead. The Venera landers were built like submarines with thick armour and limited lifespans. Most were crushed or burned within minutes, but still, they sent back images. And those images were haunting. Flat, rocky plains, broken slabs of basalt, a yellowish-orange haze that dimmed everything. There were no gentle hills, no drifting breezes, just heat, pressure, silence. Later, the Magellan spacecraft, launched by NASA in 1989, used radar to map the entire surface of Venus through its cloud layers. What it saw was a landscape dominated by volcanoes, tens of thousands of them, some as large as Earth's biggest. Lava plains stretch across vast distances, cracks and ridges snake through the crust. Venus is a world of fire hidden under clouds. What's more, there may still be volcanic activity happening now. Some studies suggest hotspots, localized areas of heat that could be signs of eruptions or magma movement. Others have seen changes in sulfur dioxide levels in the upper atmosphere, which could be evidence of gases rising from below. But it's hard to know for sure. The atmosphere is so thick, so hot, so full of mystery, that most of what we understand is pieced together like a puzzle, viewed through frosted glass. The real tragedy of Venus, though, lies in its story. Venus likely started with water. Not much, perhaps, but enough to form oceans. It may have had rain, rivers, maybe even clouds drifting through a blue sky. But as the sun grew brighter over billions of years, a normal part of stellar evolution, Venus began to warm. That warmth caused water to evaporate. Water vapour, in turn, is a powerful greenhouse gas. More vapour meant more heat. More heat caused more evaporation. A runaway cycle began. Eventually the oceans boiled away. The hydrogen from the water escaped into space. The carbon dioxide, once trapped in rocks and oceans, was released into the air, and with it came more warming, more pressure, more transformation. Today, Venus is trapped in that cycle. Its atmosphere is almost entirely carbon dioxide, with clouds of sulfuric acid that swirl in hurricane-force winds. The surface is so hot and thick that light itself struggles to pass through cleanly. There is no water left, no breathable air, no relief, and yet, somehow, it is still beautiful. The upper clouds reflect sunlight in shimmering gold. The planet's slow rotation, one day lasts longer than its year, creates strange wind patterns and a sense of languid drifting time. From orbit, the atmosphere spins much faster than the planet itself, carrying waves and spirals that ripple like silk in a storm. There is grace in the chaos, poetry in the heat. Venus is also compelling because it is so close to Earth in character. It reminds us of how fragile planetary balance can be. A few degrees of warming, a shift in chemical cycles, a change in cloud behaviour. These small things, barely noticeable over a lifetime, can accumulate over eons and reshape a world entirely. Venus may have once looked like Earth, and now it is a furnace. That's why scientists often call it a cautionary tale, not as alarmism, but as perspective. When we study climate change on Earth, we sometimes look to Venus as an extreme case, a natural experiment in what happens when greenhouse gases run unchecked, when feedback loops spiral beyond recovery. Earth is not Venus, but it could have been, or might become. And yet, despite its heat and danger, Venus still draws us in. Several future missions are planned to return there. NASA's Veritas and Da Vinci Plus missions will map the surface in high resolution and study the atmosphere's composition, hoping to learn more about its past, and perhaps why it changed so drastically. The European Space Agency's Envision mission will follow with similar goals. These are not easy journeys. The planet resists contact, but we keep trying. Because Venus holds answers, not just about itself, but about us, about what makes a planet habitable, about what makes it change, and about what's needed to protect the delicate balance that lets life persist. So now, if your thoughts are still drifting, imagine yourself suspended just above the Venusian clouds. The light is golden, filtered through sulfuric haze. The wind rushes past at hundreds of kilometers per hour, but where you float it's quiet, eerily so. Beneath you, a world glows softly, a planet wrapped in memory and heat. It is beautiful, and it is burning. A mirror turned toward Earth, not to frighten, but to remind. If Venus is the burning mirror of Earth, then Mercury is the ancient scarred coin tossed closest to the fire. It is small, just a little larger than our moon, and battered, heavily cratered, stripped of any illusion of comfort. Yet it endures. It circles the sun every 88 Earth days, locked in a rhythm where its day lasts longer than its year, with temperatures that swing from oven to ice in a matter of hours. It doesn't boast about its complexity, but look closely, and Mercury reveals itself to be more than just a rock in orbit. It is a story written in iron, time, and heat. The first spacecraft to visit Mercury was Mariner 10, launched in the 1970s. It flew by the planet 3 times, photographing just under half of the surface. Those early images were startling. The planet's face was old. There were craters on top of craters, a surface weathered not by wind or water, but by the silence of space. No atmosphere to slow impacts, no rain to wear things down, just scars upon scars, preserved like fossils in stone. Then, decades later, came Messenger, a spacecraft launched by NASA in 2004. It orbited Mercury for over 4 years and gave us a complete picture, and what it showed was far stranger than we'd expected. For one thing, Mercury has a core that's far too large for its size, about 85% of the planet's radius. That's more than twice the proportion of Earth's core. The rest of the planet, crust and mantle, is incredibly thin. Some scientists believe this suggests Mercury once had a thicker outer shell that was somehow stripped away, possibly by a colossal impact in the solar system's chaotic youth. Others think it may have formed differently, in a region closer to the sun where the intense heat favoured iron-rich bodies. Either way, the result is a planet that is in essence a metallic heart wrapped in stone, and that heart is still partly liquid, as shown by the fact that Mercury, against all expectations, has a magnetic field. It's much weaker than Earth's, but it exists. This makes Mercury one of only a few solid bodies in the solar system known to have an active magnetic field, joining Earth, Ganymede, and perhaps a handful of others. It suggests that something is still moving inside. Something is still alive, in a geological sense. The surface tells its own tale. Yes, there are craters, including enormous basins like Caloris, which spans over 1,500 kilometres, but there are also Lobat scarps, giant cliffs that stretch for hundreds of kilometres and rise up to a kilometre high. These aren't formed by impacts, they are wrinkles, folds in the crust, signs that Mercury's core is cooling and shrinking, causing the surface to compress and crack. This process continues to this day. The planet is still changing shape, ever so slightly, as it curls inward with age. And then there is the cold. Despite being the closest planet to the Sun, Mercury has no real atmosphere to trap heat. So while daytime temperatures can soar to over 430 degrees Celsius, at night, or in places the Sun never touches, temperatures plunge to minus 180 degrees Celsius. It is a place of extremes, of opposites, and nowhere is that contrast more vivid than at the poles. There, hidden in the bottoms of permanently shadowed craters, scientists have detected water ice. Radar reflections from Earth-based telescopes first hinted at it. Messenger later confirmed it. These are places so cold, so untouched by sunlight, that ice can exist undisturbed for perhaps billions of years. It's an odd thought. A world scorched by the sun where ice never melts, protected by shade, preserved by silence. That ice raises new questions. Where did it come from? Could it have arrived from comets or asteroid impacts? Is there chemistry happening in those regions? Slow, quiet, perhaps even prebiotic. We don't yet know, but these frozen patches offer a strange, hopeful contrast to Mercury's heat-blasted equator. What Mercury teaches us is not about lush possibility, but about endurance. It is a world without pretense. It doesn't hide its past. Every crater is a memory, every wrinkle a sign of something slowly turning inward. There are no illusions of comfort, but there is a kind of peace in that honesty. In the face of chaos and collision, Mercury persists. Future missions will explore more. The Bepi Colombo spacecraft, a joint effort by the European and Japanese space agencies, is currently en route, set to arrive in the early 2030s. It carries two orbiters, one to study the surface and interior, the other to map the magnetic field and exosphere. Together, they will give us an even clearer picture of Mercury's evolution, how it formed, how it changed, and how it managed to stay so strange and strong at the same time. So, tonight, let your thoughts slow, and imagine drifting over Mercury's scarred plains. The sun looms huge and bright on one side. The shadows fall deep and sharp on the other. There's no sound, just the creaking hush of metal contracting in the cold. Below, cliffs stretch like seams in old fabric. Craters gleam faintly in oblique light, and tucked in polar hollows, invisible from here, lie tiny glinting echoes of water, ice in the innermost furnace. Mercury doesn't ask for attention, but it holds it, quietly. It is a reminder that even in the most extreme places there are stories, and sometimes the smallest, most battered things endure the longest. At the far edge of the planetary family, beyond the warm familiarity of the inner worlds, and even past the grandeur of Jupiter and Saturn, lie two quiet sentinels, Uranus and Neptune. They are not easy to visit. They orbit in the deep cold, where sunlight is little more than a whisper, and the sky is always dark. Only one spacecraft has ever flown past them. Voyager 2, in its long outward journey, glimpsed them for just a few brief days each, before continuing into the void. And yet, in those fleeting encounters, it uncovered worlds unlike any other. Let's begin with Uranus, a planet so unusual that even its tilt defies expectations. Unlike the other planets, which spin more or less upright, Uranus is tilted on its side, about 98 degrees. That means for long stretches of its 84-year orbit, one pole faces the sun continuously while the other is plunged into unending darkness. A single season on Uranus can last more than 20 Earth years. It's a planet of lopsided time, where dawn and dusk stretch into decades. This tilt likely came from a colossal collision early in its history, perhaps with a planet-sized body that knocked it over. Whatever the cause, the result is a world where everything feels a little off-kilter. Its magnetic field too is misaligned, not only tilted sharply from the planet's rotational axis, but also offset from the centre. This creates a complex shifting field that doesn't behave like Earth's neat, symmetric magnetism. Instead, it warps and twists, likely generated in a layer of slushy, ionized ice deep beneath the atmosphere. Despite its oddities, Uranus appears at first glance almost serene. Its pale blue hue, caused by methane in its upper atmosphere, gives it a soft, ghostly glow. For many years, scientists believed it was relatively featureless. Voyager 2, which passed by in 1986, saw only a few faint bands and a handful of small moons. But more recent observations with powerful Earth-based telescopes and the Hubble Space Telescope have revealed something more. Uranus has storms, some the size of continents, lurking just beneath its haze. Its atmosphere may be calmer than Jupiter's or Neptune's, but it is not still. It breathes. It moves. Then there is Neptune, the farthest known major planet from the Sun. It is darker, colder, and more energetic than Uranus. Its deep blue colour, even richer than Uranus's, comes from similar methane absorption, but with a hint of mystery. The precise reasons for the colour difference are not yet fully understood. When Voyager 2 reached Neptune in 1989, it found a planet alive with motion. Winds whipped around the globe at speeds of up to 2,100 kilometers per hour, the fastest winds in the solar system. This was unexpected. So far from the Sun, with so little heat input, scientists had assumed Neptune would be sluggish. Instead, it was dynamic, a world of deep convection, where internal heat rather than sunlight drove weather systems into a frenzy. Voyager 2 spotted a massive swirling storm, similar to Jupiter's Great Red Spot, though darker. It was called the Great Dark Spot, and it captured imaginations. But years later, when Hubble looked again, the spot was gone, vanished into the atmosphere. Others have since formed, moved, and faded. Neptune storms come and go like dreams, visible, impressive, and then suddenly not there at all. Both Uranus and Neptune are classified as ice giants, a category distinct from the gas giants Jupiter and Saturn. While they share hydrogen and helium in their atmospheres, their interiors are believed to be made largely of water, ammonia, and methane ices, perhaps in a supercritical state, a kind of high-pressure fluid that behaves neither like gas nor liquid. Beneath those icy mantles there may be rocky cores, but no probe has ever gone deep enough to confirm. These planets also have rings, though far fainter than Saturn's. Uranus's rings are dark and narrow, like threads of shadow. Neptune's are more diffuse, with bright clumps called arcs that seem to defy orbital mechanics. Their moons, too, are strange. Uranus has a collection of icy satellites, many named after Shakespearean characters: Miranda, Titania, Oberon, each with surfaces etched by unknown histories. Neptune's largest moon, Triton, is a world unto itself, cold, geologically active, and believed to be a captured Kuiper Belt object, pulled into orbit and now slowly spiralling inward, destined one day to shatter or plunge into Neptune. Yet despite their intrigue, Uranus and Neptune remain poorly explored. Voyager 2's brief visits left us with questions, not answers. No spacecraft has orbited them. No landers have touched their moons. What we know from snapshots, frozen moments in time. And still, these worlds draw our curiosity quietly. Plans are being discussed for new missions, orbiters to map their magnetospheres, atmospheric probes to dive into their clouds, flybys of Triton to search for plumes and heat. But these will take decades to plan, launch and arrive. In the meantime, Uranus and Neptune wait, spinning slowly, seasons shifting over lifetimes, winds roaring through blue atmospheres under starlight we cannot see. They are in many ways the most mysterious of our planetary neighbours. Not because they hide, but because we have not yet come close enough to truly listen. They teach us patience. They remind us that distance is not emptiness, and that even the quietest members of the family have songs to sing, if only we choose to hear them. So now, as your thoughts begin to settle, imagine drifting above Neptune, where a pale sun casts a dim glow, and the winds below whisper like distant waves. Or above Uranus, tilted on its side, turning slowly, as though dreaming sideways through the cold. These are not planets that demand attention. They simply are. Beautiful, distant, and waiting. There's something special about Pluto. Perhaps it's the distance, so far from the sun that daylight is no brighter than twilight on Earth. Perhaps it's the story, once called a planet, then a dwarf, and somehow in the act of being set aside becoming even more interesting. Or perhaps it's the simple fact that, for most of our history, Pluto was just a blurry dot, a pixel in a telescope, a mystery wrapped in cold silence. And then, one day, we arrived. In July 2015, after more than 9 years of travel across nearly 5 billion kilometres, NASA's New Horizons spacecraft reached Pluto. It didn't orbit, it couldn't slow down. It performed a flyby, zipping past at over 50,000 kilometres per hour. But in that brief encounter, less than a day, New Horizons turned Pluto from a vague suggestion into a world of astonishing complexity and quiet beauty. The first image that captured global attention was of a heart, a broad pale region now called Tombor Regio, named after the man who discovered Pluto in 1930. The left lobe, known as Sputnik Planitia, is a vast plain of nitrogen ice, smoother than any expected surface, broken not by craters, but by cellular patterns that suggest slow convection beneath the crust. Beneath this frozen sheet, there may be an ocean, liquid, perhaps salty, insulated by ice. On Pluto, a world we once thought inert and dead. Along the edges of that plain rise mountains made of water ice, some towering over 3,000 metres. But because it's so cold, around minus 230 degrees Celsius, water behaves like rock, while nitrogen and methane become the snow and glaciers. These mountains are not static. There is evidence they have shifted. That ice has flowed. That Pluto is somehow geologically active, despite being smaller than our moon. And it's not just the land that surprises. Pluto has a tenuous atmosphere, mostly nitrogen, with traces of methane and carbon monoxide, that expands and contracts as the planet moves closer or farther from the sun. It's not stable. It's more like a breath, rising as the ice sublimates in summer, falling back as it refreezes in winter. The atmosphere even creates layers of haze visible in backlit images, gossamer blue bands that curve above the horizon, whispering of sunlight scattered through hydrocarbons. Then there are the cryovolcanoes, mountainous structures with deep central pits, like calderas. They don't spew molten rock. Instead, they may have erupted slushy mixtures of water, ammonia, and other ices, resurfacing the land in slow, cold waves. These features suggest that Pluto is not frozen in time. It has changed. It is still changing. Orbiting beside it is Charon, a moon so large compared to Pluto that the two bodies actually orbit a point in space between them. This gravitational dance gives Pluto a wobble, a sense of balance. Charon is also not bland. Its surface is cracked and split, scarred by ancient tectonic shifts. One hemisphere is stained by a reddish smudge. possibly from materials pulled from Pluto's escaping atmosphere and chemically altered by sunlight. Charon's surface tells of ancient stretching, of crust broken apart by internal processes, suggesting that it too may once have had an ocean beneath its crust, now frozen. It's not a simple moon, it's a companion, and perhaps a witness to Pluto's deeper story. What makes Pluto so compelling isn't just its features, it's the way they defied expectations. Before New Horizons, most believed it would be a cold, cratered rock, geologically dead for billions of years. Instead, it turned out to be diverse, layered, textured, a world with weather, landscapes, and perhaps even interior warmth. Pluto is small, yes, but it is no afterthought. And maybe that's the lesson. That size doesn't determine complexity, that what we dismiss may be the very thing that teaches us something new. Pluto reminded scientists that our models are just guesses until proven otherwise. It reminded the world that beauty can live in shadow, and it reminded us all that labels, planet, dwarf, moon, don't define wonder. New Horizons didn't stop at Pluto. It kept going, venturing deeper into the Kuiper Belt, toward other icy bodies even farther from the Sun. But its brief encounter with Pluto was a turning point, not just in planetary science, but in the story of exploration. Because reaching Pluto was about more than data. It was about touching something we once thought unreachable, about sending a message of patience, of curiosity, of determination, across a solar system and back again. Tonight, if you let yourself imagine, you might drift just above Pluto's plains. The stars are sharp and cold. The air is thin, nearly absent. Beneath you, nitrogen ice stretches in soft, pale curves, bordered by mountains of frozen water. There is no wind here, no sound, but there is movement. Slow, subtle, real. And out past the horizon, a grey moon turns, locked in step with its distant world. Two dancers in the deep dark, seen clearly for the first time. And somewhere, still drifting outward, New Horizons continues, carrying dust, data, and the echoes of a world that surprised everyone, not by being vast, but by being alive in its own quiet way. Beyond Pluto, beyond even Charon's quiet orbit, the solar system doesn't stop. It doesn't end at a line, or even a wall. It just softens. Light dims, heat fades, and the familiar rhythm of planets gives way to stillness. Here lies the Kuiper Belt, a vast scattered region of icy bodies, comets, and ancient leftovers from the solar system's youth. It is not empty. It is simply unhurried, a place where time seems to slow and motion becomes memory. After its historic encounter with Pluto, the New Horizons spacecraft continued on. Scientists had planned for this. They searched the sky and found a new destination, a small, snowman-shaped object called Arakoth. Unlike Pluto, Arakoth is not large or complex. It is barely 30 kilometers long, but in that tiny body lies something precious, pristine preservation. Arakoth is a relic, untouched for billions of years. While planets evolved, collided, and reshaped themselves, Arakoth remained nearly the same, a frozen whisper from the dawn of the solar system. When New Horizons flew past in 2019, it revealed Arakoth as two lobes, two once separate bodies that gently merged, forming a contact binary. There are no signs of violent impact, no craters of consequence. Instead, Arakoth appears soft, even delicate, like powdered sugar pressed into form. Its surface is smooth, blanketed in organic compounds known as thulins, formed when sunlight and cosmic rays interact with simple chemicals like methane and nitrogen. It is red, oddly symmetrical, and quietly beautiful. Studying Arakoth taught scientists something humbling, that planetimals, the building blocks of planets, may have formed not through high-speed collisions, but by slow gravitational gathering. Dust and rock orbiting the young sun came together gradually, clumping in clouds, dancing in spirals, until gentle touches turned into fusion. Arakoth is one of the oldest known objects in the solar system. In its stillness, it remembers how worlds began. But New Horizons isn't the only traveller heading outward. Voyager 1 and Voyager 2, launched in 1977, are still moving, still listening, still whispering across the void. After decades of planetary exploration, they left the orbits of the planets and entered something stranger: interstellar space. This is not space without stars. It is not the gap between galaxies. Interstellar space begins where the solar wind, a stream of charged particles flowing from the sun, no longer dominates. This boundary is called the heliopause, and crossing it is like stepping outside your home and realizing the breeze you've always felt is no longer there. Voyager 1 crossed the heliopause in 2012. Voyager 2 followed in 2018. For the first time we touch space not shaped by our star. Out here the particles are different. Magnetic fields come not from the sun but from the broader galaxy. The density changes, the silence deepens, and yet these spacecraft still speak to us. Their transmitters are weak, their instruments aging, but every bit of data they send is precious. Each pulse is a reminder that we have reached farther than we ever imagined, and they carry more than sensors. Each Voyager holds a golden record, a time capsule of Earth, sounds, music, greetings in dozens of languages and images of life, not because anyone expects aliens to find them, but because it felt right to send a message just in case someone someday is listening. This part of space is not well lit. It is not lively. It is quiet in ways we struggle to understand. But that quiet is not emptiness. It is waiting. The Kuiper Belt still holds hundreds, maybe thousands, of Pluto-like objects, small cold worlds orbiting in shadows. Comets rest here, some asleep for eons, others destined one day to fall inward, lighting up the sky with icy tails. And even farther out past the Kuiper Belt lies the hypothetical Oort cloud, a spherical shell of icy debris, the last distant halo of our star's influence. To explore these places fully would take centuries. We are just beginning. But even now, with just a few distant glimpses and 2 aging spacecraft crossing into darkness, we are learning something deeply human. That to search the edge is to understand the centre. That the farther we go, the more we appreciate where we began. That the edge of the solar system is not a wall, it's a question. One that asks, what comes next? And so, Voyager drifts on, carrying its gold record, its instruments, its memories of flybys long past. New Horizons glides toward the unknown, listening, for new targets in the cold, and Earth, tiny and warm, turns beneath a sky that is full of directions, each one pointing somewhere we haven't yet been. Let yourself float there now, just beyond the edge. The sun is behind you, a faint star among many. Ahead, the stars stretch unbroken. The spacecraft are small, smaller than a car, but they carry the curiosity of a species that once looked up at the sky and dared to wonder. There is no drama here, no explosions, just the slow drift of dust, the gentle hum of radiation, the hush of particles too sparse to feel. And in that hush, there is meaning. High above the surface of our world, far beyond the rush of cities, the hush of forests and the drift of ocean waves, satellites drift in silent arcs. They don't shine or roar, they glide. Tiny machines cradled in orbit, each one tuned to listen. They do not simply look down, they measure, trace, record, and over time, they've learned to watch Earth breathe. It might seem like poetry, but it's also science. From space, Earth really does appear to inhale and exhale, not in the way lungs expand, but in how its systems move together. Clouds form and dissipate, forests absorb carbon and release oxygen, ice grows and shrinks with the seasons, and from their perch in orbit, Our satellites observe all of this, constantly, gently, faithfully. The first of these watches began decades ago. Now we have a constellation of them, each with a purpose. Terra, for instance, orbits in a polar path, capturing a global snapshot of Earth's atmosphere, land and oceans every day. Alongside it, Aqua focuses on water in all its forms: vapour, liquid, frozen, flowing. Together they form part of NASA's Earth Observing System, a kind of planetary stethoscope listening for signs of change. Another, called GRACE, orbits in a pair. These twin satellites measure tiny changes in Earth's gravity field, so sensitive they can detect the mass of melting ice sheets or depleted aquifers. As Greenland loses ice, as Antarctica thins at the edges, GRACE listens, and it tells us how the weight of the world is shifting, literally. Then there's Sentinel from Europe's Earth Observation Programme. Its sensors track changes in forests, oceans and urban growth. With radar that can see through clouds, it maps flooding in real time. It captures the spread of wildfires, the scars they leave behind, and how vegetation slowly returns. It watches as glaciers retreat and deserts expand. Jason, another mission, focuses on the ocean's surface, tracking sea level rise, ocean currents, and wave heights with exquisite precision. These observations aren't just about shipping routes or coastal forecasts. They are records of the planet's heat budget, how much energy Earth retains, and how it distributes that warmth. Together, these satellites form a kind of orchestra of insight. Some look downward with optical eyes. Others use radar, microwave or infrared. They track changes in albedo, how much sunlight Earth reflects versus absorbs. They measure the carbon cycle, monitoring the rise and fall of atmospheric CO2 and methane, detecting their sources and sinks. They observe plankton blooms in the oceans and the spreading browns of deforestation on land. They track the Earth's energy balance, how much radiation comes in from the sun and how much escapes back into space. These are delicate numbers. Tiny imbalances can change climates, shift jet streams and reshape coastlines. But not all their work is abstract. Some of it is immediate. When hurricanes form, satellites scan the swirling clouds, track their paths and measure wind speeds. When wildfires rage, they trace the heat signatures and smoke plumes, helping responders predict their spread. When floods rise, radar pierces the storm clouds to see where water is pooled, where roads are gone, where people are stranded. From orbit, we can't hear cries for help, but we can see the footprints of disaster, and we can respond faster, with better tools, because of what the sky has shown us. Even plants have a signal. Some satellites can detect changes in chlorophyll, measuring the health of forests, fields and wetlands. This means we can see drought stress before leaves turn yellow. We can watch the greening of spring spread northward, year by year. We can tell which forests are growing and which are quietly disappearing. From space, life pulses. It does not shout, but it moves. Perhaps one of the most elegant observations satellites make is not of things, but of rhythms. Every year, as the northern hemisphere's forests come alive in spring and summer, they absorb carbon dioxide, drawing it from the air as they grow. In autumn, as leaves fall and decay, that carbon returns to the atmosphere. This breathing pattern shows up in the Keeling curve, a record of global CO2 measured from Mauna Loa in Hawaii. But satellites confirm the pattern from above. They show how forests in Canada, Russia and the Amazon shift with the seasons, how fires and droughts disturb the balance, how warming nudges the breath of Earth into a new rhythm. It's easy to imagine satellites as cold instruments, detached from the living world. But when you see their data, when you watch a time-lapse of glacier retreat, or a heat map of an intensifying drought, or a bloom of life in the ocean surface, you begin to realise they are not distant, they are deeply connected. They allow us to see Earth as a system, fluid, fragile, interlinked. And more than that, they teach us that even in the absence of sound, there is music. The kind of music only visible from above. A swirl of weather, a flicker of fire, the soft reflection of light off ice, a sigh in the forest canopy, a ripple in the sea. So now let your thoughts float there, above the clouds in a quiet orbit looking down. Earth is below you, turning slowly, blue, white, green, golden, not perfect, not unchanging, but at last breathing. And you are listening, not just with your ears, but with attention, with care, with wonder. If satellites have become our quiet observers, then the patterns they reveal are a kind of soft whisper, a message not shouted but persistent, one that grows clearer as the years pass, as the curves rise and as the balance tilts. From the high vantage of space, Earth's beauty remains, but it's no longer the only story we see. We're beginning to notice something else, change, unfolding slowly but unmistakably, like a tide creeping up ashore. Perhaps the most well-known signal of all is the Keeling curve. Begun in 1958 by Charles David Keeling, this simple yet profound graph records the amount of carbon dioxide in Earth's atmosphere, measured from a remote observatory atop Mauna Loa in Hawaii. It began as a line that rose and fell with the seasons, like Earth's breathing. But over time, the whole line has tilted upward, higher and higher each year. What began at around 315 parts per million is now well over 420. The rise is not steady. It has a heartbeat, a seasonal pulse, but its direction is unambiguous. From space, this pattern is no longer just a number. Satellites like NASA's OCO2 can now track CO2 from orbit, mapping where it's released, where it's absorbed, and how it moves through the atmosphere. We can see plumes from wildfires, emissions from cities, the darkening scars of deforestation. The very chemistry of the air is now visible to our distant instruments, and it tells a story of accumulation. Another signal, quieter but more haunting, comes from the polar regions. Satellites like GRACE and IT-SAT-2 have revealed a truth we cannot see from the ground, that Greenland and Antarctica are losing mass, not in chunks, not dramatically, but steadily. Greenland is shedding more than 250 billion tons of ice per year. In Antarctica, the loss is slower, but accelerating. Ice shelves that once held back glaciers are cracking, thinning, retreating. The result of this is not only seen in the poles, it's also measured in the sea. Satellites like Jason-3 and Sentinel-6 scan the ocean surface with altimeters, radar beams that bounce off water to measure its height with centimetre-level precision. What they have found is that sea level is rising, gradually globally about 3 to 4 millimetres per year. That might sound small, but added year upon year it accumulates, and it does not fall back. This rise is caused by two things: melting ice and something less visible, the thermal expansion of seawater. As oceans absorb heat, they swell. And Earth's oceans are absorbing a lot of heat. In fact, over 90% of the excess energy trapped by greenhouse gases goes into the oceans. The upper layers are warming, deeper currents are shifting, coral reefs bleach, fish migrate to cooler waters, and satellites again are the ones telling us. Beyond the numbers, space also gives us something more visceral: imagery. From orbit, we can see the scars left by fire, vast blackened areas spreading across forests, sometimes with glowing edges still smouldering. We can see dust storms rising from dried lake beds, hurricanes spiralling toward coastlines, the swelling of rivers in flooded towns. We can watch drought wither the land, fields turning from green to brown, lakes shrinking like spilled water evaporating off stone. Satellites also track extreme weather. They can measure sea surface temperatures, critical for understanding how hurricanes gain strength. In recent years, we've seen these storms grow more intense, fueled by warmer oceans. Some stall over coastlines, releasing rain for days. Others form earlier, grow larger, move faster. From space we can see their paths, and after they pass, we can see the footprints they leave, changes in vegetation, standing water, displaced soil. A storm's memory, written on the land. Even the atmosphere itself is changing. Satellites detect subtle shifts in aerosol levels, cloud patterns, and ozone concentrations. They observe how jet streams meander, how monsoon timing shifts, how the balance of heat between hemispheres varies. And as we collect more data over decades, we begin to see trends, not just events. It's easy sometimes to feel lost in this. The graphs, the numbers, the maps, the scale of it all can be overwhelming. But part of what space gives us, beyond information, is perspective. The ability to look not just at what's wrong, but at what's possible, to see how interventions work. The success of the Montreal Protocol, for instance, a global agreement to phase out ozone-depleting substances, can be seen from orbit. The ozone hole over Antarctica, once growing, is now slowly healing. A planetary wound, stitched not by nature alone, but by cooperation. That success story doesn't erase the challenges ahead, but it reminds us that the future is not fixed, that the signals we see from above are not prophecies, they are messages, warnings, invitations to act, and every signal we send back in response, every effort to reduce emissions, protect forests, shift energy, is another kind of signal, one that says, we've noticed, and we care. So now, let yourself return to orbit for a moment. Look down, not with fear, but with awareness. There is the Earth, still breathing, still moving, a little warmer, a little changed, but still rich in possibility. The curves on our graphs are not sentences, they are stories in progress, and every day we get to help write the next part. To see Earth from space is to see something fragile, not weak, but delicate, intricate, like a glass sculpture still forming in the kiln. When astronauts speak of the view, they don't talk about borders or cities. They talk about the thinness of the atmosphere, the subtle curve of the horizon, the colours, deep blue oceans, green-brown continents, white cloud veils moving, like breath across the face of the world. Many say the same thing. Earth looks alive, and it looks alone. This change in perspective has a name, the overview effect. It's not scientific in the way temperature or radiation is measured, but it's just as real. It's the feeling, reported again and again by those who have travelled beyond Earth's sky, that our planet is not just a location. It is a single, interconnected system. A home, one world, floating, turning, protected by nothing more than a paper-thin layer of air and luck. And perhaps that's what makes the final lesson of space exploration feel so personal. After all the rovers and probes and flybys, after chasing storms on Saturn and ice geysers on Enceladus, after watching methane rain on Titan and listening for sounds on Mars, what we come back to, again and again, is Earth. We look outward not just to know what else is there, but to understand what we have and how easily we could lose it. In the 1980s, the world faced a problem that, like climate change today, was invisible at first. Scientists had discovered that certain chemicals used in aerosol sprays and refrigerants were damaging the ozone layer, a fragile shield high in the stratosphere that blocks most of the sun's harmful ultraviolet radiation. As the damage worsened, a hole began forming over Antarctica, growing each spring, letting in rays that could increase cancer rates, damage ecosystems and weaken life. But this story has a rare ending in the environmental world. It was met with cooperation. In 1987, countries signed the Montreal Protocol, agreeing to phase out the most dangerous chemicals. It was not instant. It took time, but it worked. And today, satellites continue to monitor the ozone, watching it heal. The hole still appears, but it's smaller now. Less deep, less dangerous. A slow reversal visible from space. It's a reminder, hopeful and quiet, that global problems are not beyond us. They are within our power to address. And that space, which at first feels distant from Earth's concerns, actually offers some of the best tools and the clearest vision for guiding our actions. Because in the end, no matter how far we go, no matter what we find on Europa, or what Juno reveals inside Jupiter, we still have only one known world that hosts life. One planet with liquid water on the surface, with stable temperatures, with oxygen and rain, and forests that turn gold in the fall. We've scanned exoplanets, searched for habitable zones, dreamed of colonies and terraforming. But none of that changes this. Earth is the rarest treasure we've ever found, and knowing this doesn't have to be a burden. It can be a kind of gentle pride, a shared purpose. We have learned so much from space, about geology and atmospheres, about chemistry and heat, about how planets evolve and why they sometimes fail. We've seen what happens when atmospheres run away, like Venus, when water vanishes and air grows, thin, like Mars. We've studied frozen moons with oceans trapped beneath ice, and gas giants so vast they crush everything that falls toward them. And through all of that learning, Earth becomes not just familiar, but exceptional. That is the arc of exploration. We leave home to understand it better, and then, when we return, we see it with new eyes. Tonight, if you let your thoughts drift one last time through the quiet of orbit, imagine Earth as it truly appears from above, not in headlines or political maps, but as a single swirling marble of colour and light, a place where lightning dances across continents, where plankton bloom in turquoise swirls off coasts, where forests breathe and deserts whisper and snow falls in silence. You're not separate from this planet. You're part of it, made from its carbon, its water, its iron and salt and light. You are stardust filtered through a living world, and now, through the stories space has offered us, you're also a steward, not because you asked for the role, but because you live in a time when knowing comes with responsibility. Not responsibility as pressure, but as presence, a way of being, of paying attention, of remembering that the atmosphere we breathe, the ocean we float in, the ground beneath our feet, are part of a delicate and ancient balance, and that balance is not permanent. But it is worth keeping. And in the quiet, among the data and dust and distant planets, that truth returns like a soft refrain. This is our only home. It is beautiful. It is changing, and it is still alive. Far beyond the planets, past the scattered ice of the Kuiper Belt, beyond the faint gravitational tug of the sun, two small machines are still moving. They are older than many of the people now studying their data. They run on nuclear hearts and whispers of code from the 1970s. Their names are Voyager 1 and Voyager 2, and they are even now travelling through interstellar space. They are not fast by cosmic standards. They are not large or powerful or complex by today's engineering. But they are purposeful, and they are faithful. Each one carries instruments worn with age. Each one transmits signals that grow fainter with every billion kilometres. And yet, when the dishes turn, when we listen, they still speak. They were not designed for this. Originally, they were built to tour the gas giants, to swing by Jupiter, Saturn, and in Voyager 2's case, Uranus and Neptune. That mission alone would have secured their place in history. But after their planetary work was done, they kept going. No brakes, no turning back, just a continuous arc into the unknown. Somewhere along that arc, they became something more than probes. They became symbols. Each Voyager carries something no other spacecraft has carried before or since. A golden record. It is a phonograph, an actual analogue disc, etched with sounds and music and greetings in 55 languages. A child's laugh, a heartbeat, a kiss. Waves breaking, Buck Blind Willie Johnson, Peruvian panpipes, The recording was made not because we believed aliens would find it, or because they'd know how to read it, but because we wanted to send something beautiful, something kind, something that says, we were here, and this is what we valued. You can imagine those golden records now, still spinning slowly in the dark, encased in aluminum covers, glinting faintly in the starlight that almost never reaches them. They will likely outlast the Earth. They're quieter than prayer and more permanent than monuments. They are, in a sense, bottles in a cosmic ocean, cast not in desperation, but in curiosity. And that's what space exploration has always been at its best. Not conquest, not dominance, but long, careful reaching. A question stretched out across distance. A gentle knock on the door of a universe that mostly does not answer. These machines drift farther every day, powered by the last warmth of their power sources. One day, those power sources will fade. One by one, the instruments will go silent. First the magnetometer, then the plasma wave antenna, then the transmitter itself. Eventually there will be no signal, just silence, not failure, just the end of breath. But what a breath it has been. They've shown us moons we didn't know existed, volcanoes erupting on Io, ice cracks on Europa, Neptune's swirling storms, Uranus's eerie sideways spin, and after all that they've entered a realm we had never touched, the space between stars, and still they listen. They measure the density of particles, the orientation of magnetic fields, the absence of solar wind. They do not expect applause, they simply keep going. Their signals, though weak, are measured in minutes and hours of light-speed travel. Each message we receive is old by the time it reaches us, and yet it always feels timely. Sometimes the ground teams point the dishes toward them, massive radio telescopes turning slowly to track the arc of two ancient travellers. And as the data arrives, just a few bits per second, it feels like a postcard. Faded at the edges, but unmistakably personal. There is a kind of peace in this, a stillness. Not all machines are restless, not all signals are urgent. Voyager reminds us that movement does not always mean noise and that presence can exist without immediacy. New Horizons, too, is still out there. Having flown past Pluto, it continues into the Kuiper Belt, still listening, still searching. One day, it too will fade, but for now, it glides on, another lightless craft in the dark. And this is how the solar system holds on to its stories. Not in monuments, not in fanfare, but in machines that drift, quietly, steadily, lovingly, sent by a species not content to look up. A species that needed to send something forward, something hopeful, something tender. So now, as you lie still and breathe slowly, you might imagine these tiny craft, smaller than cars, older than the internet, sailing through a space so empty it might as well be sleep. They do not blink, they do not steer, they simply go, past the solar wind, past the known, past everything we once imagined as boundary. And somewhere on one of them, a record spins in silence, and somewhere on that record a baby cries, and somewhere far behind it all Earth turns, still sending out signals, still listening, still wondering. And now, with the night deep around you and the journey nearly complete, we return, gently, to where we began. Earth, a blue whisper beneath stars, a turning cradle of cloud and salt and song, not the centre of the universe, not its origin, but something just as rare, a place where the universe woke up, looked around, and began to wonder about itself. You've travelled far tonight, across deserts on Mars, into the ring shadows of Saturn, through the storm belts of Jupiter and the icy echoes of Neptune. You've drifted above methane seas, hovered near nitrogen plains, listened to seismometers and solar panels, watched light scatter through hazy atmospheres and golden haze swirl around frozen moons. You've stood beside ancient rivers that once flowed across red dust. You've climbed water-ice mountains on Pluto, and you've floated, quiet and still, with spacecraft that no longer feel the sun. But now, let's circle back. Not with a bang or a flash, but a memory. Earth was always there, waiting. In every image taken by those machines, the background, the reflection, the source of every question asked. When Voyager 1 looked backward for the last time, it captured what would become one of the most iconic images in all of science, the pale blue dot. In that photograph, taken from over 6 billion kilometres away, Earth is less than a pixel, a dust mote suspended in a sunbeam, and that mote, that speck, is everything we know, everyone we've ever loved, every meal, every poem, every heartbreak and every discovery. Carl Sagan, who helped inspire the photograph, wrote that this image underscores our responsibility to each other and to this fragile world. Because Earth is not guaranteed. It does not endure untouched by time. We've seen this. On Venus, where a runaway greenhouse effect transformed a once Earth-like world into a furnace. On Mars, where atmosphere fled and rivers dried into memory. On Titan, where chemistry whispers of what might have been. On Europa, where oceans hide in darkness, waiting perhaps for a touch that never comes. The solar system is not hostile exactly, but it is indifferent, and that indifference makes Earth's balance all the more precious. The more we explored, the more we saw how rare our conditions truly are. A magnetic field to deflect solar wind, a stable atmosphere with just the right mix, liquid water not frozen or boiled away, a large moon to steady the seasons, plate tectonics to recycle nutrients, biodiversity that seems to defy odds, and minds that not only wonder, but build, send and remember. So what do we make of all this? Perhaps it's not about answers. Perhaps it's about belonging, about seeing ourselves not as above nature or separate from the universe, but as one expression of it. The solar system, vast and old and cold, somehow gave rise to warmth and thought and language, and tonight that journey has circled back to you, not as a conclusion, but as a reminder. You're part of a planet that looked outward. That didn't stay still. That turned curiosity into technology, that wrapped metal in fire and launched it into the sky, just to see what was out there. You are part of a species that attached a golden record to a machine and let it drift forever, not because it would be found, but because it meant something to send it. And perhaps most gently of all, you are part of a species that watches storms from orbit, listens to tectonic hums, counts photons scattered by ice, and reads the breathing patterns of forests, not because it must, but because it can. In this great unfurling, you're not small, you are placed, positioned in a moment, yes, but also connected, by memory, by molecules, by meaning. So as you lie there now, quiet and wrapped in your own orbit of thought, you can let go. The solar system will keep spinning, the probes will keep drifting, the clouds will move across the Earth's surface, whether you're watching or not. That's the wonder. You're allowed to sleep, to rest, because the universe is not demanding. It simply is. And somewhere in that quiet turning, your place remains. You don't have to chase it. It won't disappear if you stop thinking for a while. It's part of you. You carry it. You carry the dust of stars and the memory of oceans and the shape of your world's gravity in every breath. And whether your eyes are open or closed, whether your thoughts are bright or fading, you're held in gravity, in time, in curiosity. Sleep well. The universe is vast, and it is still whispering.